joining us for this fourth video in the chapter about reactions of alcohols. This may seem like a little deviation, but we want to talk about reactions of ethers, which we made right previously from alcohols. By the way, in this video, I've been thinking about like how the video screen's kind of small because of the portrait. Maybe I should have done this from the beginning. Let me know if you like this format of the video where it's like a full width. Anyway, there's not very many that many reactions ethers can do. These are fairly inert functional group. So you kind of need to have a pretty extreme conditions to make them react, and one of those uses it has to use not just the acid but strong acids, I should say. Maybe it has to be a strong acid, like hydroiodic acid. That doesn't say hi or Hawaii. Remember, is one of the strong acids from Chem, right? Like this could fragment the ether into two fragments, and it's also not a super new reaction. This is once again just a variation of SN2 reaction. The way this works, if you have a very strong acid, of course, right, the lone pair of the ether could pick up the proton, and then what happens, of course, is that this oxygen now becomes a good leaving group, right? And the iodide that is left behind, remember, that's actually a pretty good nucleophile, and so for that reason it could do an SN2 reaction like so. Right, this is a good nucleophile. And maybe I could just kind of skip drawing the product again. That becomes the product here. Now, there is a regiochemical concern here, and that word just has to do with which part of the molecule, which location of the molecule reacts. And the iodide technically could have attacked this carbon to kick this off, ethanol, or this carbon to kick this isopropanol off. And can you guess why the regiochemical preference? Right, and that just simply has to do with the fact that this is less hindered side of the ether, which leads to the regiochemical preference. So you don't get the product where the iodide attacks. That is the point. Okay. Now, here's another example. Here we have a cyclic ether, and I want you to see if you can predict the product in the class. We'll do that together, this example. Now, another example of ether reactions is opening of the ethers, but through basic mechanisms. But when it comes to a basic condition, something like this, for instance, if you subject this to the same condition, it's not going to open. The ether is a very inert reaction. The only reason why the basic condition can open a three-membered ring or epoxide is because it's got a ring strain, right? So maybe I'll say and the sterics decide the regiochemistry. Okay, so we'll take a look at that. So Well, let's first think about the mechanism of this, right, to predict the product. That's one major theme in our class and also in the future exams, that you should be able to predict the product of a reaction if we supply you with the starting material and some reagents. Now, how do you predict the product? You have to think first about the mechanism. Okay, so how do you think about the mechanism? Well, here's think about what kind of reagents and species you have, right? Here's a good, strong nucleophile. Here's an epoxide with an angle strain, which means it wants to open. Okay. Now, which side, right? That's going to be the question. So, remember, this is going to be an SN2 reaction essentially. Here, nucleophile attacks, and then oxygen is going to act as a leaving group, which it's not a great leaving group, but it's assisted by the ring strain, and that's why it works. Okay. Ring strain. Okay. Remember, nucleophiles prefer to attack less sterically hindered site, which would be this over that, and so attacks that carbon, this oxygen leaves, so this is an SN2 reaction. So that would be the product. Now, when you draw a product structure, right, you should always make it neutral. So how do you make this neutral? Well, this alkoxide could pick up a proton from the methanol solvent, which is abundant, and once it does, it's going to be whoops, I think I added an extra carbon. Right, that would be the product. Okay. The take-home message here is it's driven by angle strain. And it needs to also be driven by a very strong nucleophile, like alkoxide. Okay. Here's another example that I want you to think about, and this one I might actually go over with you right here. So the lithium aluminum hydride, remember, that's a good nucleophile, nucleophilic hydride source, right? And that's what that does. And so the product, actually maybe stop the video here, see if you could predict the product. It's gonna look like this. And we want to think about why that's the case by thinking about the mechanism. So that's aluminum hydride. Here's the substrate. Right, which side is more less hindered? Of course, it's this site, this carbon, not that carbon. So what's going to happen is the hydride anion would attack that, opening the ring this way, right? And that would end up with two hydrogens here. Okay. I should say technically, right, we could be specific that hydride from the aluminum hydride would come in from the front face, so I could say that. And then that's the product of the first step. Now in the second step, that's what we would call aqueous workup. You sort of quench the reactive species in the reaction by adding water and sometimes often like some acid, and HCl in water would dissociate to become, and then the water would pick up the proton to become hydronium ions. That's the main acid you're dealing with, and this would now lead to the product. Okay. Now, can you open the epoxide? Can you open epoxides under acidic condition? And it turns out you can. And here the deciding factor is regiochemistry factor. Deciding factor is going to be which carbon has more partial positive charge. That's going to be the deciding factor. Okay, so this is very similar to the earlier example, but it's going to open at the different site. So the product is going to look like this. It's very different. So let's examine the mechanism to understand why. So if you have, if you put in HCl, technically I should say that would protonate the solvent first, so that's likely the acid that encounters. Now if you put HCl here, I probably wouldn't mark you off unless we're specific about the acidic species in the problem, but technically I want you to know that would be the acid species that you would encounter. Now, so it gets protonated, that's a pretty strong acid still. Right, so now you have this positively charged epoxide. Now, because it's positively charged, this oxygen is now really thinking about leaving behind the carbon. Now, if it's going to leave a carbon or a carbocation, which one do you think it would leave behind? Primary or secondary? Of course, it would be the secondary, right? So between these two carbons, this is the carbon that's feeling the partial positive charge more, because this carbon still is kind of in a secure relationship with this oxygen, but not this carbon. So he's feeling the partial positive charge more than the other. Hope that makes sense. And so if you have weak nucleophile like alcohol, right, what it's going to attack is, of course, the one with partial positive charge, because otherwise weak nucleophiles like this cannot act as a nucleophile unless there's an electrophilic carbon. So once again, this is SN2 though, and so for that reason it's going to happen through the backside attack leading to inversion. So this methanol would have attacked from the backside. So I'm showing that here, and we could have the solvent pick up that extra proton to become the product. Okay, so the take-home message here is that more substituted carbon bears the partial positive charge more. Now you might be thinking like, if it's a nucleophile, wouldn't it want to attack the less hindered carbon? Well, yes, if we could, but this carbon is not at all electrophilic, and so weak nucleophile would never attack it anyway. Okay, here's another good example that I want you to think about. This one perhaps we'll do in class. Okay. Now the last reaction I kind of want to talk about with the ether is kind of a public safety announcement of a sort. Here's diethyl ether, which is often abbreviated like that. If you expose this to air or oxygen, it could form a peroxide through radical mechanism that we won't go over right now. Technically, after chapter 3 that we're going to go over at the end of the semester, you could figure this out, but so the functional group we're referring to is this peroxide. Every time you have two oxygens bonded by a single bond, that's a peroxide, and then this is a notoriously weak bond, and so for that reason this can fragment. Once it fragments, becomes this very unstable reactive species that reacts with just about anything in an explosive way. So this is very explosive. Okay. Another thing often happens even more readily with THF, the same reaction. The alpha carbon, or the carbon bearing the ether, often gets peroxide like that through air exposure, and both of these are very explosive. So what does that tell you? You should not leave ether bottle open to the air. You're just waiting for an explosion. Now, I want you to know that most of the ethers you might be using in your OChem lab would probably have a peroxide inhibitor to inhibit this oxidation reaction, but you never know. So just be careful how you handle ethers. You should not let it be exposed to the air. Okay.